What we want to look at now is something called the entropy of mixing, and let's look at a container that has a membrane separating two gases. They'll both be at the same temperature and pressure. So if I take a tank or something like that, and I'll have two things, the temperature and pressure in each one is the same, and here I'll have Na and Va. So I have the A molecules occupying volume A, and the B molecules occupying volume B. And we're going to let TA equal TB equal T, and we're going to let this be adiabatic, so there's no heat transfer going on, so there's no heater work. So if I remove this membrane, what's going to happen? So if I remove the membrane, then the A is going to go over here, and the B is going to go over here, and we have all this stuff mixing around. So it's going to be mixing around, and I can find the change of entropy for A and B. And in general, S2 minus S1 is equal to N C sub P bar times the log of T2 over T1 minus N R bar times the log of P2 over P1. And we have initially that PA equals PB is equal to P. The total pressure remains the same. So we have the temperature and pressure remaining the same. So when I look at this, the temperature, when I remove this, the temperature doesn't change. So this term goes out. So this term goes out. So now I'm going to evaluate the change of entropy for the A molecules. So I'll have del S A is equal to minus Na R bar times the log of PA over P. So this PA is the final pressure. So PA, now these gas molecules have gone everywhere. So PA is the partial pressure of the total pressure. So now the total pressure P is made up of PA and PB. So this is equal to Na R bar times the log minus times the log of Ya. And del SB is minus NB times the log R bar times the log of YB. The entropy production, the total delta S, the total change for the system is the sum of the del SI, which is positive. So we're going to see that this is greater than 0. Because we have the log of a fraction, log of YB is negative, and I have a negative here, so I have a negative times a negative. So this term is a positive, this term is a positive, and so I have this entropy change, this entropy of mixing. So this is the entropy of mixing. It's totally irreversible. You can't unmix. So once you did this, there's no way to get the A's and the B's back separately again. So it's a totally irreversible process. But now, let's say that I changed this and I said, I'm going to let these things be the same, but now I'm going to, let's say, that Na is equal to air and Nb is equal to air. No, air has two different things. Let's make it oxygen and oxygen. O2 and O2. So I'll let it be the same gas. So now I have the same gas in both places. So I have the same gas here as here. And if I remove the membrane, these molecules are going to go over here, these molecules are going to go over there, so they're not as contained as they were, but I can't figure out the partial pressure because I can't distinguish the A molecules from the B molecules. So for entropy of mixing to occur, it requires the concept of distinguishability. Distinguishability. So if I don't have distinguishability, I'm not going to have, if I don't have that, then I won't have an entropy of mixing. And so it's a special case, but it's sort of interesting when we think about entropy and a measure of disorder. And so we can see that it has that, but if I can't distinguish the disorder, I can't calculate the change of entropy. Now let's do a couple of examples. We'll find the entropy production, things like that for mixtures. And we'll have mixtures coming in. We're going to find the entropy production, etc. So it'll be a more complicated problem. So let's say we have two streams forming a third stream. In here we'll have 50 cubic meters per minute. It'll be air at 40 degrees C and 101.3 kPa. So this will be A. So I'm calling this A. Often I call them 1, 2, 3, but for some reason I'm doing A for air. And then I'm going to pick helium here. So I have helium, 20 cubic meters per minute at 100 degrees C and 101.3 kPa. In the mixture, so here we have the mix, and it's at 101.3 kPa. So the total pressure does not change. And what we want to find is the temperature of the mixture, as well as the entropy production, and we want to find the mole fractions. So we'll find the mole fractions as well. So we want to find T mix, del S dot production, and YR. So we're interested in finding that. And so we can find the mass flow rate. So first we'll find the mass flow rate. So we have, as we know, we have an open system. It's adiabatic. And we have mixing going on. And so the mass flow rate for the air, m dot air, is PV dot over RT. So I have 101.3 times 50 over 60. Again, I need to get things on a second basis away from minutes. Divided by R, 0.287 times 313 degrees K. So I have the mass flow rate of the air is equal to 0.9397 kilograms per second. I'll do the same thing for the mass flow rate of the helium. So the mass flow rate of the helium is equal to PV dot over RT is 101.3 times 20 over 60, again seconds, the helium 2.077, and the temperature is 373. And so I have the mass flow rate of the helium is equal to 0.0436 kilograms per second. XA is equal to 0.9397 divided by 0.9833 is 0.955. So 95.5% of this mixture is air, and the balance, X helium, is 0.045. And now what I want to find is I need to do this switch to the mass basis, so I can find the mole flow rate of the air is equal to the mass flow rate of the air divided by the molecular weight of the air. So I'm putting it on a mole basis. So I have this as 0.9397 divided by 28.97. So that's equal to 0.03034 kilogram moles per second. So anyway, we have it on kilogram moles per second, and we do the same thing for the helium. So n dot of the helium is equal to the mass flow rate of the helium divided by the molecular weight of the helium is equal to 0.045 divided by 4.003 is equal to 0.0109. So YA is 0.0324. Oh, there wasn't a zero here. Couldn't read my own handwriting. 0.0324 divided by the total number of moles, 0.0433. So YA is equal to 0.748, and therefore YAT is the difference between that and 1, 0.251. So what we found, the first thing we found was we had to find the YA. We wanted to find that as one of the things we needed to find. And now we wanted to find the mixture temperature.